Hello and welcome back. Today we're going to learn about independent events. In statistics, independent events are a little bit different than what you might think, and people get confused about this sometimes, so I'll do my best to try to explain this. But in class tomorrow, I'll go over any questions that you have. Independent events occur when the probability of one event has no effect on the probability of another event. Okay? If the probability of one event occurring has no effect on the probability of another event occurring, what we say is they are statistically independent events. The way we're going to test for independence is by this formula. If the probability of A given B turns out to be the same thing as the probability of A, then that provides the conclusion that A and B are independent. Okay, so that's the test for independence. Now, recall from last lesson that the probability of A given B, there's a formula for that. So essentially what you're doing is you're doing the probability of their intersection divided by the probability of B has to equal the probability of A in order for those events to be independent. And if you really think about this, this kind of does make a little bit of a sense. Okay, if you have two events A and B, if you're looking at the probability of A given B, that means you're looking at their intersection divided by the probability of B. Now if that intersection, the probability of anything in there occurs, is the exact same thing as the probability of A, then really B had no effect on the event A occurring. Okay, so that's what independent means. Now what you'll notice, even though this is technically the test of independence, I can rewrite that in a form that's a little bit easier to work with by multiplying both sides by the probability of B to give me the probability of A and B is equal to the probability of A times the probability of B. So if you multiply those probabilities and you get the same thing as the intersection, then that's another way of saying that you have independent events. Okay, pause the video, write down anything you need to. Okay, so look at some examples. Number one, determine whether or not A and B are independent given their probabilities. First, let's set up a Venn diagram. They're in terms of probabilities, but you can write down percents if you wish. Okay, just make sure they correspond. I'm going to use probabilities because that's what I'm given. So first fill out the intersection, 0.2. That means the remainder of A must be 0.2 because all of A must be 0.4. And the remainder of B must be 0.3 because all of B is 0.5. And then the outside, make sure you account for everything, the total. Notice this is a total of 0.7, so I have to have another 0.3 that's in neither A nor B. Okay. So we have to test to see if they're independent or not. So we're going to see if the probability of A given B, is that equal to the probability of A? And if it is, they're independent. If they're not, then they're not. Probability of A given B is going to be their intersection, 0.2, divided by the probability of B, which is 0.5. You want to see, is that equal to 0.4? Now, if you do this in your calculator, you'll see that 0.2 divided by 0.5 is 0.4, and that does equal 0.4. So, yes, A and B are independent. Okay, yes, they are independent. Now notice, like I said before, another thing you can do is you can test, if you multiply probability of A times probability of B, that's 0.4 times, that looks horrible, 0.4 times 0.5, which is 0.2, which notice is the intersection of A and B. Okay. That's sometimes like the shortcut method of finding if they're independent or not. Just multiply their probabilities right away and see if they end up being equal to the probability of the intersection. Okay, let's look at number 2. In a class, 50% of students are female, 60% have brown hair, and 35% are female students with brown hair. Okay. So let's set up a Venn diagram. So we have 2 events, being female and having brown hair. Look for the intersection, so 35% is the intersection. That means the remaining 15% of the females don't have brown hair, and the remaining 25% of the brown hairs are not females. Let's add this up. So I have a total of 75, it looks like, so I have to have another 25% outside. So you want to know, are the events being female and having brown hair independent of each other? So let's test that out. We want to see, is the probability of being female, given that they have brown hair, is that the same as the probability of being female? So the intersection is 35 divided by brown hair, which is going to be 60. Is that equivalent to, now notice we're dealing with probabilities, right? So this is going to be between 0 and 100. So probability of being female is really 0.5. Okay. And if you divide that out, you'll see that you get 0.583 repeating, and that's not equal to 0.5. So these are not independent. Okay. The probability of one is affected by the probability of another, so they are related in some kind of way, okay, given the sample that we have. Pause the video, write down anything you need to. Number 3. Now this is an example where I give you some data arranged in a tabular arrangement of values. Okay, so we have to use this to help interpret how to find certain probabilities. So, a poll was taken, 300 voters were asked if the coverage of a recent debate was satisfactory. The results are below. So let's first note, we do have totals for each row and for each column, so it might be helpful to separate those by drawing lines. Okay. First, have some practice just finding some probabilities. Find the probability of event S occurring, that you're satisfied. Okay. So, how many people are satisfied? Well, a total of 135 out of a total of 300 voters. So that will give you the probability of being satisfied. Type that in your calculator, you get 0.45. Now to find the probability that you're satisfied given that you're female, so we're just going to look just at the female data. We have a total of 200, and of that 200 that are satisfied with the results are just the 80. So 80 divided by 200. Calculate that out, you get 0.4. Okay, now let's look at the probability of that you're satisfied given that you're a male. So we're just looking at just the males. So we have a total of 100. And the ones that are satisfied of the males are the 55. Okay, that's a pretty easy one to calculate, 0.55. All right, let's look at letter D. Are these events satisfactory and male? Are those independent events? Justify your answer mathematically. So you want to know, is the probability of satisfactory given a male, is that equal to the probability of being satisfied? Now we already calculated those above. We can note that 0.55 is not equal to 0.45. So no, they're not independent. Okay, so we can use tabular arrays to help figure out probabilities. Pause the video and write down anything you need to. Alright. One more example. 70% of the class watch the World Series game. 50% are on the school's baseball team, and 35% of the students watch the World Series game and are on the school's baseball team. Are the events independent? Sorry, let me read it again. Are the events watching the World Series and being on the school's basketball team independent? Okay, so let's create a Venn diagram. So maybe World Series is one, baseball team is on the other event. Okay, on the other circle. So I have three numbers. 70% watch the World Series, so inside this circle for World Series should total 70%. 50% are on the school's baseball team, so and 35% is the intersection. So I'm going to write 35 as our intersection. That means the remaining of the World Series watchers is 35, and 15 is the remaining baseball team players. That totals up to become 85, so there's another 15% that's in neither of those. Okay, so you want to know, are they independent? So you want to know, is the probability of watching the World Series, given that you're on the baseball team, is that equal to the probability of the World Series, watching the World Series? So the intersection of those is 35 divided by the probability of being on the baseball team, which is 50. Is that equal to the probability of watching the World Series, which is 0.7? Okay, and if you do 35 divided by 50, you get 0.7. That is equal to 0.7, so that is true. Yes, they are independent. Okay, let's pause the video, write down anything you need to. Okay, so today we looked at a concept called independent events. And it's just basically saying if you have the probability of one given another, if it's equal to the probability of the first, then they are statistically independent. So if their intersection of A and B given B, so over B, if the probability of A given B is the same thing as the probability of B, of A, then they are independent. Yay, they're independent. Okay, so thank you for watching, and we will go over any questions you have in class. See you tomorrow.